This exercise presents information on drive geometry. Drives that we will look at include traditional hard disk drives, solid-state drives, and flash memory. Traditional hard disk drives are mechanical drives because they contain moving parts. HDDs rely on spinning disks or platters to read and write data. The technology for these mechanical drives has been around for over 50 years. Since that time, they've become smaller, faster, as well as increasing their storage capacities. A hard disk drive uses an actuator arm with read-write heads that move over one or more magnetically sensitive platters. The structure of an HDD is broken down into sectors, tracks, and cylinders. Solid-state drives, or SSDs, are not made this way. In this image, you can see tracks, sectors, and cylinders, and you can see the read-write heads that are moving over the spinning platters that is controlled by the actuator arm. A hard disk drive spinning platter will stop under the actuator arm at places when data is stored. Data can be written to either the top or bottom. You may find that a platter is also referred to as a head, hence you will see CHS, meaning cylinders, heads, and sectors. Tracks are concentric circles, and a sector is part of a track. A cluster is several sectors. Sector sizes are 512 bytes. When data is stored, space is allocated for that data, so a cluster is assigned to any given file. Even if the file only needs a few bytes, the entire cluster is allocated. Drives have unallocated space. This is important to note when analyzing sources of deleted data. This graphic shows two clusters with one file stored in this space. The two clusters are allocated for that one file and cannot be used for other files. So even though part of Sector 6 and all of Sectors 7 and 8 are not needed, the space remains unused. Slack space is that leftover space. When a file is deleted, it is not removed from an allocated cluster. The file system has an index, and when a file is deleted, the index reference is removed, but the data will still be on that cluster space until it is overwritten. So even though data is deleted, it may still be in unallocated space or slack space. Unallocated space, also called free space, is defined as the unused portion of the hard drive. File slack is the unused space that is created between the end of file marker and the end of the hard drive cluster in which the file is stored. You will find that sometimes suspects will store data in unallocated space or slack space. To overwrite all data on a drive completely, you do a drive wipe. A drive wipe has different levels, but in effect, a pattern of ones and zeros is written repeatedly over the entire disk. Another term that you need to be familiar with is a transistor. A transistor is a microelectronic component that acts as a switch and amplifier for electric current. Now, you do not need to be an electronics engineer. However, you need to be familiar with the term because a transistor is the basic component where data is stored on a solid-state drive and flash memory. The switch is either an on representing one of two states indicated by using the binary number system. 0 represents an on state or current present, and 1 represents an off state or no current present. This is important to know when analyzing deleted data that might be found on a solid-state drive and flash memory. You also need to consider that when a drive wipe is performed, a series of ones and zeros is written across the entire disk, ensuring that there is no data left over on the drive. NAND flash is a type of non-volatile memory that is accessed like a mass storage device. It's called NAND because at the circuit level it's similar to the NAND logic function. This is at the circuit level. The N in NAND means not and. Non-volatile means that data is retained when there is no power. Now, you do not need to be an expert at the circuit level with transistors, NAND logic functions. You should be aware of some of the terms though. NAND flash memory also applies to USB thumb drives. That's why we refer to USB thumb drives as flash memory. You should also understand that the NAND function is part of the transistor, and recall that the transistor is the basic component of how data is stored, represented as ones and zeros. One of the other things that we'll take a look at is that the transistor is called a cell when you look at deleted data on a solid-state drive. NAND flash memory is used in USB thumb drives and solid-state drives. This graphic shows how the memory is structured. The cell is where the transistor works, where current is applied or not applied. hence the 1 or 0 either having data or no data. Transistors are embedded into a chip. There are a lot of transistors in any given chip. In this image, you can see a chip which has millions of transistors on a USB thumb drive. This is why a USB thumb drive is also referred to as a flash drive. Solid-state drives are made up of NAND flash memory. They consist of cells, pages, and blocks. A cell is the basic component of the solid-state drive. This is the transistor. Pages consist of cells. A block consists of pages. The cells are arranged into a grid. All of this is in a chip. Solid-state drives can have several chips. Solid-state drives read and write data a cell at a time. However, when data is modified, deletion occurs. Deleted files are removed in the file system index, but the data remains until erased. Solid-state drives erase a block at a time. What happens is an entire block that is modified is copied to a new block, and the old block is entirely erased. In the world of solid-state drives, the term slack space receives a new meaning. Rather than being a matter of files and cluster size alignment, slack space in solid-state drives deals with the different sizes of minimal writable and minimal erasable blocks on a physical level. In SSD terms, pages is the smallest unit of storage that can be written to. The typical page size of today's solid-state drives is between 4 kilobytes or 8 kilobytes. Micron, the manufacturer of NAND chips used in many SSD drives, published a comprehensive article on the SSD structure. You can view this article by visiting the website listed on this slide. While a page is the smallest unit that can be written to, a block, on the other hand, is the smallest unit of storage that can be erased. Depending on the design of a particular SSD drive, a single block may contain 128 to 256 pages. This means that a deleted file with a size less than a block will remain on the block until the block is erased. This may seem inefficient, and there are routines that address this issue, such as a garbage collection algorithm and a trim command up to certain file sizes. In practical terms, this means that files or file fragments, chunk sizes less than 512 kilobytes or less than 2 megabytes depending on the solid-state model, may not be affected by these routines and may still be forensically recoverable. Another SSD technology is deterministic read after trim protocol. This addresses file fragments not cleaned up by the trim command or the garbage collection algorithm. This protocol is implemented on many recent solid-state drives and makes trimmed pages inaccessible via standard SATA commands. Because of this, the actual data may physically reside on the drive for a long time, yet it will not be available to forensic specialists via standard acquisition technologies. Sending the solid-state drive to the manufacturer might be the only way of obtaining this information on a physical level. So what does this have to do with digital forensic imaging? There are different extraction methods, such as logical and physical, which will be discussed in a subsequent exercise. Deleted data of evidentiary value may be found in unallocated space, slack space, or in the case of solid-state drives, left in a block before it is erased. Not all extraction methods will extract data from these hidden spaces, and not all tools are equal. That is why imaging tools need to be verified against standards and be able to do successful physical extractions and be supported by the software vendor.